We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Now, BBC One investigates a landmark in space exploration that's out of this world.
August 1977. A radio signal confirms contact with a spacecraft called Voyager. Thus began a journey to worlds beyond our wildest imagination. To planets that looked like stars. With moons of fire and ice trapped in a cosmic tug-of-war. To miniature solar systems surrounded by breathtaking rings that belie a violent and devastating past. Voyager would uncover strange invisible magnetic fields and reveal the cataclysmic events that continually reshape our solar system. On worlds billions of miles from the sun, it would witness a drama of creation never seen before.
Voyager will stand out as the mission which has visited more new worlds than any mission before, and I think any mission after will ever do.
Those aren't little dots of light in the sky. Those are real bodies. They're interesting places out there, and they're real.
Every time we turned around, we were getting more new, exciting data, pictures of places that we hadn't imagined.
There's a lot of variety, a lot of uniqueness. Every world is not alike.
Going to worlds never before seen by the human species. There's something chilling about that, something exciting. It makes the heart beat faster.
Outbound on one of the greatest adventures of the 20th century, Voyager carried the hopes and dreams of a generation of scientists and engineers. Join us now as we salute the bold spirit of innovation that made it possible. Sail on, Voyager. The road to the stars begins at the foot of the San Gabriel Mountains in Pasadena, California. Caltech's Jet Propulsion Laboratory is the nerve center of NASA's planetary exploration program. Here, Earth got the first close-up look at its nearest neighbors. Beginning in the 1960s, a generation of probes called Mariner took us to Mercury, Venus, and Mars. By the end of the 1970s, the time had come to explore the outer planets.
Goldstone, I would just like to confirm you have acquisition of Voyager signal.
That's affirmative at 1649.15. We have receivers in lot.
Earlier, two Caltech students working at JPL, Michael Minovich and Gary Flandreau, saw a rare opportunity. For the first time in 2 centuries, the outer planets would be aligned on the same side of the sun. A single spacecraft could encounter Jupiter, go on to Saturn, rendezvous with Uranus, and finally call on Neptune. The mission was nicknamed the Grand Tour. But Washington would not approve the budget. JPL proposed a compromise, known as Voyager. Two spacecraft, Voyager 1 and a backup, Voyager 2, would go to Jupiter and Saturn. Uranus and Neptune would become an option. Caltech professor Edward Stone would lead the scientific team.
We were indeed fortunate that our technology was ready, because this grand tour, this alignment, occurs only once every 176 years. And if it had occurred 10 years earlier, we probably would not have been ready to have taken advantage of that opportunity.
A journey to the outer planets covers a staggering 4 billion miles. The task of finding the right flight path or trajectory fell to mission design manager Charles Cole Hayes. He and his team would sift through 10,000 possible choices.
When a trajectory designer looks down at the solar system and watches the planets all orbiting the sun, taking different numbers of years to go around, he sees opportunities to go from the Earth to Venus, to Mars, or to the outer planets. But those opportunities only occur at specific times when the planets are in the right positions. In the case of the Voyager trajectories, we had to wait for the right time. We needed some way to reach these remote planets with a sizable payload. That came through a method known as gravity assist, a slingshot effect.
For a spacecraft, a planet can act like a natural fueling station in space. The two Voyagers will depart Earth each on a slightly different course. As they approach Jupiter, their speed will increase as the planet's gravity hurls them around like a slingshot towards Saturn. There, Voyager 1 will fly by Saturn's moon, Titan, and then leave the planets. If Voyager 2 receives the go-ahead, it will continue on to Uranus. Flying by Uranus will boost its speed by nearly 5,000 miles an hour and alter its course for Neptune. The accuracy required to reach this remote planet has been compared to a golfer sinking a putt 1,000 miles away. With exacting skill, it will be the closest flyby of the mission. The journey to Neptune from Earth would normally take 30 years. With an assist from gravity, Voyager will make it in 12. As Voyager's first project manager, Bud Schermeyer was chosen to make it happen. Now retired and an avid glider pilot in his spare time, he is a veteran of the early days. In the 1960s, Schermeyer directed the Ranger probes that put America into the race to reach the moon. Later, he guided Mariner 6 and 7 to Mars. Until then, the importance of photography in planetary exploration was uncertain. But the role of cameras on future spacecraft was assured by powerful images from Mars and the Moon. For Bud Schermeyer, Voyager was an even greater challenge.
The decision as to what experiments would fly and what scientists would be principal investigators on the mission involved a very time-consuming and long and sophisticated process. The first chore was to pick the team members. The key team members at that time consisted of the spacecraft system manager, when I selected Ray Heacock, who I had worked with in Ranger and Mariners and knew very well.
Heacock would develop the most intelligent spacecraft yet built. Voyager could virtually fly the mission by itself, although its 3 onboard computers were less powerful than today's PCs.
Any good, PC today is going to have several 100,000 words of memory, and no one would think of buying a computer with the limited capabilities that the Voyager systems have. And of course, today, no one is thinking of building for spaceflight computers of such limited capability. But the thing that these computers had was reliability. And being programmable through ground operations, we can still have it perform very complex and sophisticated operations. 11
science instruments aboard Voyager will survey the planets. They will detect particles and magnetic fields. They will probe rings and atmospheres, measure their temperatures and wind speeds, and determine chemical composition. The remote sensors and high-resolution cameras are mounted on a fully movable scan platform. Voyager was also designed to withstand the rigors of deep space and of launch. Cape Canaveral, Florida, August 20th, 1977. Charles Cole Hayes remembers.
We launched Voyager 2 first, and it got underway okay. And then several days later, in early September, we launched Voyager 1. Well, when we launched Voyager 1, and this huge Titan Centaur rocket left the launch pad, what happens is the Titan, the solid rocket's thrust for a while, and then the center liquid stage thrust, and it gives the Centaur all the speed it can. The Centaur then goes into a circular orbit around the Earth. It fires its engines, and we finally get underway. Well, while we were all at the Cape, we noticed that the Centaur had used 1,200 more pounds of propellant to get into this coasting orbit than it should have used. And we realized there had been a malfunction in the Titan burn. Basically, the fuel and oxidizer had not mixed at quite the right ratio. And when it finished its job, it had not given the Centaur enough speed. Now the question was, does the Centaur have enough fuel left to fire up again and get us underway for Jupiter?
If not, the spacecraft will lack the speed to catch the trajectory to Jupiter. The dream of a grand tour hangs in the balance.
The bottom line on that is it made it, but it only had 3.5 seconds of fuel left in the tanks. It did have a normal guidance shutdown. 3.5 seconds later, the tanks would have been empty.
The troubled launch is an omen of things to come. Although the two Voyagers are safely on their way, problems continue to arise. Preoccupied with Voyager 1, JPL forgets to send a routine command to Voyager 2. Without the command, the spacecraft assumes its radio receiver has failed and switches over to the backup. But the backup proves tone-deaf and can't lock onto the signal. By controlling the frequency of the transmission from Earth, the ground crew tries desperately to re-establish contact.
Data chief has to configure this, but this is actually what we are getting in here.
Goldstone, I would just like to confirm you have acquisition of Voyager.
Finally, Voyager responds. But the faulty radio would handicap the spacecraft for the rest of its journey.
Receivers on, signal level -145.
March 1979, Voyager 1 approaches Jupiter. It has been a year and a half since launch. Now a rendezvous with a giant planet seems destined to become reality. Brad Smith of the University of Arizona was head of the imaging team throughout the mission. Although scientists have observed Jupiter for centuries, Voyager's first glimpse of the planet was full of surprises.
We were surprised by just about everything we saw. When we started our first encounter with Jupiter, we thought we knew the answers, we thought we knew what we would see. One thing after another turned out to be not what we expected. During those hours around closest approach at Jupiter, when the very highest resolution pictures were coming back, we were filled with awe, elated, in some cases worried, concerned in that the complexity was so much greater than we could have imagined. There was a certain feeling while we were so delighted with such a rich harvest of science, a certain amount of almost despair as would we ever be able to interpret, to understand what we were seeing.
Voyager revealed Jupiter's turbulent atmosphere in stunning detail. Bands of clouds swirl around the planet, and the great red spot churns like a mammoth typhoon. First observed in the 1600s, this huge storm system is 3 times larger than Earth. After nearly 4 centuries, it still rages. Jupiter spins on its axis twice as fast as Earth. Wind speeds exceed 300 miles an hour. Opposing jet streams create spirals and eddies that appear and then evaporate. Other storms are trapped in perpetual motion. Imagine a world without continents, only oceans of liquid hydrogen and helium. Above, winds roar without ceasing. Storms too violent to comprehend rarely abate. Clouds shimmer and crackle with lightning. Such turbulence had never been envisioned. Jupiter's dynamic atmosphere was a revelation, but the biggest surprise was yet to come. Voyager would visit 4 of Jupiter's moons. Countless collisions with asteroids have obliterated the surface of Callisto. Without geologic activity to erase them, each scar is testimony to a long and tortured past. Europa is deceptive. Its terrain appears rugged and cracked, but these features are an illusion. Locked in an ocean of ice, they are actually smooth and flat. Ganymede, the largest moon in the solar system, is also battered. But jumbled blocks of ice the size of continents and faults reminiscent of the San Andreas suggest that geologic processes were once at work here. But of all Jupiter's moons, none was more startling than Io. Its surface was surprisingly smooth. At first, Brad Smith was concerned.
Io, a satellite which was to be a Rosetta Stone in the outer solar system. It was going to be covered with craters. It was going to tell us the age of the solar system, the activity in the outer part of the solar system, and no craters. As we got closer and closer, still no craters. We realized that something was covering up that surface, and the surface of Io was getting younger and younger as we got closer and closer.
Four days later, the mystery would be solved. Today, in her spare time, Linda Morabito Hyder writes science fiction. But when Voyager encountered Io, she was a member of the navigation team. March 9, 1979 is a date she'll never forget.
It was a Friday, and it was 4 days after the encounter, closest approach. And I was doing my job in order to determine to a higher accuracy the orbit of Io. So this was after the encounter had taken place and the press conferences were over, and the members of the science team were basically on their way to take a rest and had decided a break was in order, and probably felt that most of the wonders that Voyager showed us had already been encountered. And it was in doing my job, I saw something off the limb of Io that I knew didn't belong. What I saw was a very large object off the edge of Io. Now this large image, initially one would think it would be a satellite, another satellite that was unintentionally captured by Voyager, but it was much too large to have not been seen before.
Her discovery would make headlines. It was the first time an active volcano had ever been seen beyond Earth. Captured on the limb of Io, its immense plume rises nearly 200 miles above the surface. Eventually, 8 more active volcanoes would be found. What could cause such an incredible display? Jupiter's massive gravity keeps Io locked in orbit. But as the moon Europa passes, it also pulls on Io. Trapped in a gravitational tug-of-war, its surface bulges and flexes. The constant flexing of Io's surface generates heat, melting the moon's interior. As the heat escapes, it produces what may be the largest volcanic eruptions in the solar system.
If I had to pick a single highlight for the mission, I would pick the volcanoes on Io, because that was the discovery which was so unexpected that it really opened our eyes. We had to take our blinders off. We recognized at that point we were no longer going to be able to anticipate what we were going to be seeing.
And then the final revelation. As Voyager prepared to depart, it took one last picture of Jupiter. There, backlit by the sun, was a ring never seen before, a fitting end to a visit full of surprises. In its brief encounter, Voyager revealed more about Jupiter than had been learned in the entire history of astronomy, and sent home over 30,000 images. The images are taken through a series of color filters. Candy Hansen of the imaging team combines the different images to reveal the planet's true color.
We didn't move the scan platform.
In August 1980, Voyager began observing Saturn.
All right, there it is.
All right, yeah.
Yeah, you can tell.
Pointing's good, even.
Yeah.
Actually see that
Yeah,
it's a planet.
you can recognize it, yeah.
Saturn is famous for its beautiful rings, but the first images show little detail. As Voyager closes in, resolution improves. Hansen will exaggerate the color to make the planet's features clearer for study. Now, the full spectrum of Saturn's beauty begins to emerge.
The first pictures we got were about as good as Earth-based pictures from a good observatory. And then as you get closer and closer, and the planet grows in the picture and gets larger and larger, we started to see more and more detail in the clouds. We started to see more and more belts and zones in Saturn's atmosphere. But the really exciting, dramatic thing were the rings.
New and unexpected rings orbit Saturn like a carousel. Where did they come from? How are they formed? How old are they?
What are planetary rings?
Larry Esposito lectures at the University of Colorado.
Around the planet Saturn, these particles form a ring, each in its individual orbit.
A member of the Voyager team and a specialist in the new science of planetary rings, Esposito shares a theory.
Here in this table I have a rock representing the planet Saturn, and around it some pieces of chalk that represent small moons. These were probably formed all at the same time, at the origin of the solar system. And these moons are subject to bombardment by meteorites and asteroids. The meteorites which strike these moons can occasionally break them up. The material in these moons is broken up into smaller pieces, each in orbit around the planet. And as all these particles are moving around, another moon will be smashed. And those particles follow their own orbits around the planet. What happens to these rings? Well, the small material is charged by electrons and is pulled off by the magnetic field of the planet. Some of it is dragged in by the atmosphere and ends up in the planet itself. Eventually, the rings that we're seeing here in 1 million years are gone. But there are still more moons around the planet, and these we continually break up to make new rings.
The notion that rings are the product of violent ongoing collisions is dramatic enough, but more discoveries were in store.
In 1980, as Voyager was approaching Saturn for the first time, I went to a meeting and I saw one of my colleagues with some photographs very close to his chest showing other people. And what he was showing was that there were dark lanes on the rings that looked something like the spokes of a wheel. And I sort of snuck over and got a look too. Of course, everybody knew within a month that this new phenomenon had been discovered by Voyager, that the rings had not only striations in a circular sense, but it had finger-like projections that could be seen. And these radial finger-like projections were called spokes. The spokes turned out to be very tiny particles, particles the same size as the particles in cigarette smoke, about a 10,000th of an inch in size, that had been lifted above the rings. And these tiny particles lifted off the surfaces of other particles were what we saw as spokes in the rings. We know what they are, but we don't know now how they came to be.
Bathed in a perpetual glow, the rings seem to overshadow the planet. But with each encounter, Saturn itself grows more intriguing. Cold and distant from the sun, its clouds are obscure. Winds blow 3 times faster than on Jupiter. A turbulent ball of primordial gas, Saturn resembles a miniature solar system. Of its 18 moons, 4 were seen for the first time by Voyager. Composed of rock and ice, they are made of the stuff of comets. Most, like Tethys, are littered with craters. An impact on Mimas nearly blew it apart. Rhea and Dione are only partly cratered. Perhaps they were resurfaced by ice melted by internal heat. But none is more alluring than Titan, the only moon with a dense atmosphere. Voyager confirmed that Titan is steeped in organic material, the precursors of life. Astronomer Carl Sagan hoped the pictures would tell the story.
Voyager 1 was dedicated to make a very close flyby of Titan, the fabulously interesting big moon of Saturn. But to do that, we had to lose the option of Voyager 1 getting to Uranus and Neptune. And what I was hoping for was that the clouds that surround Titan might have breaks in them. And if we got very close, high-resolution camera might be able to see through the breaks and see what the surface of Titan was like. Fabulously interesting world, because organic matter is falling from the skies like manna from heaven, and it certainly seems today that it has a great deal to teach us about the events that led to the origin of life on Earth 4 billion years ago. But as it turned out, there were no breaks in the clouds. We took hundreds of high-resolution pictures that had nothing in them, no detail whatever. Every world was a surprise. Not a one of them conformed closely to our vague expectations.
In 1980, its mission accomplished, Voyager 1 leaves Saturn to head for the stars. With the success of the encounter, a decision is made. Voyager 2 will go on to Uranus. Designed for a 5-year mission, it is already 4 years old. On August 26th, disaster strikes.
Just after we flew at our closest approach to Saturn, with Voyager 2, the spacecraft which was now due to go on out to Uranus and then Neptune, I got a call about 3 o'clock in the morning that the scan platform was sticking and it stuck. We were losing Saturn data every minute. But worst of all, that same spacecraft that was supposed to go out and give us views of 2 new planets was in very great trouble.
The cameras are pointing in the wrong direction. The Voyager team at JPL is staring at empty space.
Ellis has drawn what you should be seeing.
Your frame's upside down.
Lift the slew end times out of the S. Okay, the slew end time.
Finally, a solution.
What they did was to back it up a little bit, like a stuck car trying to get out of the mud or snow. They go this way and that way, and this way and that way, and eventually they freed it up. And in fact, they freed it up in time that we did not lose all of our Saturn data. There were still some observations that we were able to make before we left the Saturn system.
Ahead of Voyager lay a daunting 5-year journey. Uranus is twice as far from Earth as Saturn. Communication with the spacecraft will now be a challenge. Radio signals must travel across 1 billion more miles of space. Nothing could be done to strengthen the signal from Voyager. Its reception on Earth had to be improved. Dick Laser was project manager during the upgrading of the communication system.
Good day, John.
Hello, Dick. Good. Welcome back to the Mars site.
Thanks. Good to see you again. Hey, what I'd like to do today is take a look at the new X-band transmitter at...
In California's Mojave Desert is JPL's Goldstone Deep Space Communication Center, one of 3 tracking stations located around the world.
The spacecraft itself, and in fact even our ground system on the ground, wasn't prepared to handle a spacecraft that would be as far away from the Earth as Voyager 2 would be when it encountered Uranus. And so we embarked on a plan to overcome the effects of distance. Okay.
We're
so
up
here
on
we are.
this surface now, and then we'll be looking into the cone and some of our electronics that we have.
Until now, each antenna has been sensitive enough to receive Voyager's transmission.
Whoops. Tippy here.
But finding a radio signal from Uranus will be like looking for a needle in a cosmic haystack. Like a car radio, the further it gets from a station, the weaker the signal. For Dick Laser, the feeble transmission from Voyager would compound the problem.
The data transmitted from the spacecraft is transmitted through a radio receiver, but not with thousands of watts like your radio or television station, but the transmitted power is just a few watts, less power than the dim little porch light you may have sitting out in front of your house. And when it's received at the stations on the ground, the received power is on the order of about 1/20 the amount of power required to power my digital watch.
JPL's engineers would find an innovative solution.
A technique called arraying was devised, where in fact rather than making the ear bigger, the antenna bigger, several antennas were electronically connected together so that in fact the effective hearing or listening area would be larger, and that was called arraying. At Uranus, we would arrayed together 1, 2, 3, 4 antennas down in Australia, 3 antennas here at Goldstone. At the Neptune encounter, the array here in the United States was truly massive because we arrayed together the 27 antenna array down at in New Mexico, the very large array VLA.
To overcome the low amount of sunlight at Uranus and Neptune, the spacecraft itself would have to be re-engineered, its computers reprogrammed. JPL's foresight a decade earlier would now pay off. Edward Stone recalls.
Extending Voyager's reach beyond Saturn was a real challenge because we were going to extend the operation of the spacecraft 3 times further from the sun than had originally been designed for. Out to where the sunlight was only 1/9 as intense as at Saturn, and where the signal coming back to Earth was only 1/9 as strong. So we had to make a number of changes. For instance, we had put on the spacecraft a special coding device called a Reed-Solomon coder, which today is in everybody's CD player, but at that time was a very innovative coding system. We had never turned that coding system on until after Saturn. We needed it because in order to go on to Uranus and Neptune, we needed a more efficient way to code the data coming back to Earth. We also had to learn how to stabilize the spacecraft so that we could take longer exposures and not have smear. And so we developed a number of techniques on the spacecraft to make the images more stable as we had to have longer and longer exposures in the more distant reaches of the solar system.
The challenges of upgrading the spacecraft, upgrading the ground, and the extra challenge caused by the failure of the Voyager 2 scan platform. And what we went through to assure ourselves that, number one, it worked, and number two, it would get the job done at Uranus. All of those challenges really kept us very busy during those several years and made the time fly by very, very quickly.
In January 1986, 8 years after launch, Voyager approaches Uranus. On Earth, the modifications have been successful. The signal from Voyager is loud and clear. Radio emissions from Uranus confirm the presence of a magnetic field. But it is unlike anything the scientists expected.
Planetary magnetic fields are generated by the flow of electrically conducting material deep inside the planet. In the case of the Earth, it has to do with the molten interior of the Earth, which generates our magnetic field. Now on Earth, Jupiter, Saturn, even Mercury, the poles of the magnetic field are very near the rotational pole of the planet because presumably the currents tend to be associated or formed by the rotation of the planet. We had a major surprise at Uranus where we found the magnetic poles were down near the equator of the planet.
Uranus is tipped on its side. The magnetic poles are tilted 60 degrees away from its rotational axis. The planet's rotation electrically charges its hot, fluid core, generating a magnetic field. But at Uranus, the magnetic field is offset from its center. Because of these odd alignments, the solar wind sends the planet's magnetic tail spiraling through space like a gigantic corkscrew. At JPL, excitement runs high as the first images begin to appear. But an atmospheric haze obscures the view. Still, Uranus radiates large amounts of ultraviolet light, a phenomenon JPL dubbed dayglow. As Voyager skims over the equator, attention turns to the 5 major moons. Most are small and cold, like Oberon and Umbriel, ancient worlds of rock and ice pummeled by cosmic debris. On Ariel and Titania, the dominant features are global faults and cracks. But on Miranda, the bizarre is commonplace. Here, almost every exotic terrain Voyager has seen is jumbled into one.
All these clouds around, I don't know what we're going to get.
Planetary geologist Eugene Shoemaker and his wife Carolyn specialize in asteroids and comets. They know that collisions play a key role in shaping the solar system. Tonight they are at Mount Palomar in Southern California. Here, at the 18-inch telescope, they will search for objects that might one day cross Earth's orbit.
Okay, well, let's hope that tonight's the night for a new comet Shoemaker. It's about time.
39 degrees, 35 minutes.
By carefully aligning the telescope, a series of photographs are taken of the same area over a period of time.
That looks good.
When the photographs are compared, they can see if an object is moved. If so, it might be a comet. This work has led Gene Shoemaker to a theory about Miranda.
Here's an icy satellite with peculiar blocks of terrain on its surface, patches that are just distinct, that are young features geologically, some roundish in outline, some rectangular in outline, that represent a localized spot of geological activity. And the question is, how would this come about? How would it happen that you have these funny blocks of terrain and not reprocess the whole surface of the satellite? Now imagine that Miranda, when it was first formed, was warm, and the rocky constituents settled to the core, and the ices settled to the outside. So you had an icy mantle and a rocky core. Now you smash the satellite up into pieces that are scattered just randomly in the orbit, and then they're reassembled without regard to whether they were once in the core or once in the icy mantle. So you'll have big chunks of rocky material, big chunks of ice. As the satellite warms up again, those chunks want to find their proper home. The rocky part, which is denser, wants to go to the center, the icy parts to the outside. You could get melting, you could have eruptions at the surface, and you could form a local feature, such as these very strange patches that we see on the surface. So I think we're seeing the evidence on the surface of the inside of the satellite trying to get back to its proper and original configuration after its last catastrophe.
Following the fatal collision, Miranda's fragments stay in orbit around Uranus. Over time, the debris is pulled together by gravity and begins to reassemble into a moon. A patchwork of ice and rock, its interior begins to warm. Melting ice flows onto the surface to form a unique new landscape. Miranda has been the highlight of the Uranus encounter. As information continues to stream in, the spacecraft is bound for its next rendezvous, 3.5 years away. Neptune, the final and outermost planet on the Grand Tour. Its most prominent feature is a giant spot. Seen for the first time by Voyager, it is similar to the one on Jupiter. The presence of a storm surprised Andrew Ingersoll, an atmospheric scientist at Caltech. The amount of sunlight that reaches Neptune is equivalent to twilight on Earth. Because energy from the sun drives weather, this dynamic atmosphere was totally unexpected.
The big surprise for me was that here you have this planet Neptune, way out in the solar system. It receives a few tenths of a percent the amount of energy that the Earth does, and so you'd expect the weather to be dull. And what do we find? It's the windiest planet in the solar system. Storms are moving around at speeds of 1,400 miles per hour. It's, if Columbus had had winds like that, he would have crossed the Atlantic in a few hours. It was amazing, simply amazing.
To study the weather on Neptune, Ingersoll and his colleagues developed a computer model of its atmosphere.
Not changing at all. And then this is...
Where does it come from?
Hi,
Where did
Andy.
this come from? Hi, Andy. Oh, I got some good stuff here. I think you can see the 1,400 mile per hour winds on this great dark spot.
You're going to prove it to us?
Oh, you'll believe. What you have to do is to look at the little white clouds that are scudding across the top of it.
Looks like it's doing
Okay, yeah, like this
rotation.
one.
Yeah, and of course, it's a little hard to see because they jump so much from one image to the
Yeah,
next.
you never see them right at the top.
You're
Well,
never
you do,
you're never
actually.
sure you're seeing the same cloud, but
Yeah.
but when you play it fast, it all just kind of gels and you realize what's happening there. Watch them go now. They're just ripping across there. Look at that one. The computer models that reproduce the complicated behavior that we see have a couple of common elements. Obviously, they don't have continents and oceans, so there's nothing for the storms or the winds to rub against. But in addition, they have very little friction. These are atmospheres without turbulence. If you start something in motion, it just goes on forever. If you start winds in motion, they go on forever. It does all the things that the real thing does. Look at it.
You know, that's great.
This is hydrodynamics here. The only thing I'm still worried about is this great dark spot actually rolling, or is it just kind of rocking back and forth? Now,
Just oscillating.
yeah, I mean, is it rocking or rocking or
Rocking or
rolling? That's the
rolling.
question. All right.
Without friction, there is no turbulence. So Neptune's dark spot rocks continually back and forth like a pendulum. But what could cause the high winds?
I think I understand that now. As you turn down the energy supply, you reduce the friction, and that allows the winds to build up. You reduce the turbulence. It sounds simple now, but it sure was a surprise when we first saw those winds.
A violent storm on a cold and sunless world. Howling winds that defy logic and humble the intellect. Were more surprises still in store? In Flagstaff, Arizona, a branch of the U.S. Geological Survey is solely devoted to the growing field of space geology. Geophysicist Larry Soderblom is interested in Neptune's largest moon.
I need some Triton data. It's a PA tape. I need 494 mounted on iFlight 2. Sure. Okay, thanks.
Triton is one of only 3 moons in the solar system with a permanent atmosphere. Voyager sent back 2 sets of images to create a mosaic of Triton. Where they overlap, the features appear in 3 dimensions.
The spacecraft was flying past Triton, so one set of images would be acquired from one angle and another set from another angle. If we could look at those in stereo, it was possible to see what was on the ground and what was above the ground. The 2 images were projected onto a sphere. And they're shown in this view. One of them is in red, one of them is in green, and so features that line up are shades of yellow. And you can see up in this region, all the features seem to line up pretty well, with the exception of 4 major features here. And in fact, this is where we first noticed the active geysers. If we blink the 2 images, you'll see these dark markings dance across the surface, whereas the others are locked onto the surface, perfectly registered.
What Soderblom discovered are giant plumes of gas rising from a field of nitrogen ice on Triton's surface.
Fairly sure that a process in which heat interacting with the nitrogen ice, raising the temperature only a few degrees, can cause the nitrogen to evaporate very rapidly. This will cause gas to flow into subsurface reservoirs, kind of like a giant gas field. And the gas that's coming off that warm nitrogen ice is much higher pressure than the nitrogen gas that's in the atmosphere. So if this reservoir is ruptured, the gas rushes toward the open vent and carries aloft fine carbon material, very fine particles we call foo-foo dust. And so the dark foo-foo dust is caught up in the winds and strewn out downwind to the west about 150 kilometers in the case of this geyser.
Plumes of gas erupting from geysers on a frozen moon at the very edge of the solar system. Triton would be a fitting climax to the Grand Tour. At 5:14 in the morning, on August 25th, 1989, Voyager 2 bids farewell to Neptune and heads into deep space. A 12-year, 4 billion-mile odyssey finally comes to an end. 6 months later, on Valentine's Day, Voyager 1 turns its cameras on for a last look at our distant family of planets.
Well, today marks yet another milestone in Voyager's exploration of the solar system, the completion of mankind's first picture of the solar system from beyond the outermost known planet.
Well, I like this distance. This is the furthest any observed.
Most distant picture ever taken by the human species.
Earth appears but a tiny point of light.
There's no real science in such an observation, but to look back and see our tiny, and I tell you, truly insignificant Earth sitting there in the blackness of space, and to take an image of it from out near the edge of the solar system, it's emotional.
Voyager is destined to wander among the stars. Bolted to its side is a gold-plated record. On it is a message from mankind to any alien intelligence. It says, "This is a present from a small and distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so that we may live into yours. We hope, someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe."
Здравствуйте, приветствую вас.
धरती के वासियों की ओर से नमस्कार.
Siani bingalela makawe, sinipisela inkonzo ende. Ria Dumelisa Marena.
Hello from the children of planet Earth.
BBC One continues its infinite voyage tomorrow morning at 9:05 to find answers to questions such as what does an atom look like and why do stars shine?